Welcome to ECEN 403-404, Senior Design. Today's lecture will be on microcontrollers and basics of embedded. So today we're going to be looking at an introduction to microcontrollers, the selection of microcontrollers, some general basics regarding them, looking at the different operating systems that you can run on a microcontroller versus like embedded Linux, Android, or just doing something as we know as bare metal, where you just write the application for the microcontroller and it runs, and some of the common pitfalls that you're going to find with your embedded project. So first of all, let's just jump right in. What is a microcontroller or a microcontroller unit, an MCU? Well, in simple terms, it is a small computer that is effectively a computer on a single IC. Now, this has kind of morphed over the last 20 years. It's kind of originally started out as a processor solution of multiple chips, then it became a single chip solution, and now it's morphed into still kind of a single chip solution, but with still a lot of companion ICs that you can add. So primarily a microcontroller includes RAM, some sort of program memory built in, basically like flash today would be a case, your read-only memory, and then various peripherals such as general purpose I/O, GPIO pins, digital I/O, UARTs, which if you're new to this class and you're just getting into your project, you might not know what a UART is. A UART is basically known as a serial port. Stands for Universal Asynchronous Receiver Transmitter. And this is basically a simple communications mechanism to transmit data serially, one bit at a time. You would have learned about this in some form or fashion in 248 or 350. So your laptop has USB ports, a universal serial bus, and you can use a serial port adapter off of your USB to give you true UART port access. Then there are things like analog digital converters, where you're going to take an analog signal and convert it into a digital form, sample it. If some of you have had ECEN 444, digital signal processing, you're going to know a little bit about what that is. But if you haven't, you're likely to use this because if you're trying to read any sensor technology, such as like a temperature sensor, a pressure sensor, or the like, then you're going to want to convert that analog waveform that you get out of those sensors into a direct digital signal that you will do some sort of intelligent processing on. And then vice versa on that is a digital to analog converter. You have some numerically computed value. You now need to represent it as a voltage, maybe to drive an amplifier that's going to drive a speaker, or to drive a servo motor, or to drive a valve of some kind. In that case, you would actually be using a digital to analog converter to do that. Then there are some general purpose interfaces for communicating from chip to chip, like I was talking about a moment ago with kind of the basics of a microcontroller processor. Is you usually have other peripherals you would hang off of the processor, for instance, the additional A to D converters are a more precise one, doing some sort of specialized function, such as a touch sensor interface, or humidity sensor, so on and so forth. You can actually get specialized ICs that do a specific task, and you would actually want to communicate that data digitally, but you don't want to use a bunch of I/O pins to communicate that information. So you use something like the SPI bus, the serial peripheral interface, which was invented by Motorola, and then you have the I2C bus that was invented by Philips, also known as the SMC bus, because Philips actually trademarks and holds the basically claim and trademark to I2C, but it's a real common data interchange format, and so competing technology that uses the exact same protocol and bus format calls themselves the System Management Bus or SM bus. You can also have various timers and peripherals, such as pulse width modulation. If you don't remember with pulse width modulation, probably from your 248 class, it is basically where you have a waveform, a digital waveform that has a set period of a certain frequency, say, let's just say 1,000 hertz. And then you turn on and off the on time versus off time. So that period is a set time. And then depending on how much time on, so if you did 1,000 hertz, or basically you have 1 millisecond period. If you did a half a millisecond on, or 500 microseconds on, and 500 microseconds off, or a half a millisecond off, that would be 50%. And of course, if you had 250 microseconds on and 750 microseconds off, it would be 25%. That is highly used in like heater control, servo control, all sorts of mechanism. Everything uses your LEDs in your backlight of your laptop and your smartphone are controlled typically using some form of pulse width modulation. You also use things like timers for timing events. I mean, it seems simple to say, but if you want to know how many pulses per second you're getting off of a motor, say an encoder that's on a motor, to know how many revolutions per minute the shaft is actually turning for some sort of control, like speed, for instance, or position, you would use a timer counter input to actually do that, and you'd actually precisionally time events and also count events. In this case, count pulses over a period of time. Say like, how many pulses did I get over 1 second, or how many pulses did I get over 100 milliseconds, or something along them lines. So microcontrollers actually date back to the late 1970s and early 1980s. One of the very first microcontrollers that actually came out that was specially built for the purpose of being an dedicated peripheral processor that in itself, the actual IC itself did all of the functions, had all the RAM and all the ROM. It's not a, again, this is, we're not talking a microprocessor solution where you have a separate microprocessor, you have separate RAM, you have separate ROM, you have separate all your interfaces, and really the microprocessor is just the processing interface. A microcontroller, again, is a one-chip solution typically, where all the peripherals, all the RAM, all the ROM are built into one chip. So one of the first ones was the Intel 8048, which came out with the first IBM PC in the early 1980s, and it was actually the keyboard controller. So you had this big clunky keyboard, and you have all the keys on your standard QWERTY keyboard, and you had a Intel, and that time was an Intel 8088 XT processor. Actually, the PC was prior to the XT. So you had this PC processor, and then you had this basically a matrix keypad. So you have all these keys that had to be monitored, and to know which key was pressed, they used actually another microprocessor, a dedicated microcontroller in this case, the 8048, to monitor the keypad, to monitor the matrix of rows and columns to determine which switch was pressed, and actually tell the main processor, the Intel 8088, that, oh yes, the word letter Q was pressed, or the enter key was pressed, or the number one key was pressed. So the idea was you had one little microcontroller that just monitored all of these I/O pins, doing a row column switching. If you ever want to learn about that, please ask me. So you do row column, you energize row to monitor a column, see if a key was pressed, and you can do quite a few keys with very few I/O lines by doing that. And so that's what they actually did. That morphed into the 8051. In fact, you can actually see here the copyright date on this 8051 family was 1980. And this was the first major microcontroller that kind of hit the industry in the 80s and 90s. Kind of revolutionized embedded systems, actually. Personally, I cut my teeth as an embedded systems engineer on this microcontroller. One of my friends actually owned a compiler company, started it in his basically in his apartment on a card table, kind of the old story of how some of the businesses get started and become worth millions of dollars. Well, I actually witnessed this firsthand with one of my friends, and he built a compiler company from the ground up, supporting the 8051 family was the processor that they were targeting. That morphed into various different families, the Intel C51 family, the Siemens, and became Infineon, and a few others. And eventually they got bought out by ARM because they targeted the ARM compilers for the ARM processors, and they were a really good compiler company. By the way, the name of that compiler company is Kyle Software. If you're ever done any embedded development, you might have seen their tools. So, and again, this became a very popular microcontroller, built on quite a few embedded systems over the years, from voting systems, strangely enough, to sort ballots and count ballots, for instance, in the voting industry, motor controllers to weigh scales, etc. Process controllers for oil and gas were built on 8051s. The original one, and I have used the original one, only had 128 bytes of RAM. Hard to believe. 128 bytes. That's not even 128 kilobytes, not megabytes, not terabytes. 128 bytes, single bytes. So you can imagine if you only had 128 bytes of RAM and 4 kilobytes of ROM, how, well, let's just say how studious you had to be, how efficient you needed to be as a programmer and creative to be able to do some complex tasks. I've actually have done some complicated processing of some algorithms to determine, settings of certain oil, gas, and servo valves and things like that, all with an Intel 8051, one of the original ones, and it is non-trivial to do that. You get very creative to determining how to do scaling of your math so that everything can still be integer math and not floating point math. Because floating point, if you remember from doing ECEN 350, floating point math is very expensive in the sense of computational cycles and also the amount of code it takes up to support that format. It's not a big deal today with the modern microcontrollers we have now, but back, 30 years ago, this was a big deal to deal with floating points. So it got very creative. Quite frankly, in my personal opinion, I think as an embedded systems programmer, I have become sloppier and lazy um, in my programming versus what I used to be back, 20 some odd years ago, because back then I was limited by my hardware, and so I got very creative and very efficient. Nowadays I've got, kilobytes and megabytes and gigabytes worth of space to deal with. If I'm on an IMX6 or an IMX8 64-bit ARM processor, and I have 4 gigabytes of flash for file space for application layer, and I've got, probably a couple gigs of RAM as well, I don't really care if I'm being very efficient and using double precision floating point versus single precision versus unsigned integers. I'm not too concerned with performance typically. So it's a great era to be in as a developer because you've got all these resources, but it also does make you a little bit sloppy. So the code I look at today, I'm using double precision floating point when I really probably could get away with unsigned integers, but it, to the end goal, it doesn't really matter. So again, this had 128 bytes of RAM, 4 kilobytes of ROM. We only had 12 clock cycles per instruction. So remember, again, from 350, we mostly talked about an ARM processor that had 1 clock cycle per instruction. In fact, with proper pipelining and proper paralleling of your cores, you would end up with fractions of a clock cycle per instruction. So this actually took 12 separate clock cycles. In fact, a typical 8051 that I worked with, we would clock it at 12 megahertz, so you would actually get a 1 megahertz performance or 1 MIPS out of the processor, which again, 25 years ago was quite a processor. Um, it only had one UART and 2 little timers. And of course, over the years, over the period of the when the 8051 was in its heyday, so to speak, when it was really popular, the processor evolved and expanded. The license on it was given out by Intel to other manufacturers. The patent eventually expired as well, and eventually it ended up the whole line of different microcontrollers were available with all sorts of different peripherals, Ethernet controllers, USB controllers. Just everyone was gluing something onto the Intel 8051. Only problem is it was an older architecture, and it made coding in them difficult. As I've just recently have had to relive, I have a project that I have going on right now, actually, in which, and as it's a core, it's an Intel 8051 processor, and I haven't used one of these in like 15 years, effectively, especially in a production environment. And I had to relearn, some of the quirks of Intel 8051 architecture again, and I was kind of cussing it a few times. It's just very frustrating device to use some days versus some of the more modern microcontrollers. Another very common microcontroller at the starting net era as well is the microchip PICs. You'll see that in this class, I usually ask you to, if you're going to think about getting your feet wet and actually using an actual chip-based microcontroller, I usually lean you a little bit towards the microchip PICs because they are very easy to use. I mean, typically you apply power, ground, maybe a crystal oscillator. You don't even need that. Basically, power and ground. It's effectively almost like a chip you would have used in ECEN 248, power ground, and boom, you're up and running. Um, Programming it, you usually need a small little programming pod of just a few pins. And then the embedded software tools are very easy to use. So PIC stands for Peripheral Interface Controller. And again, like the Intel 8051, it began its life as a peripheral device for, in this case, DEC mini computers. So back in the 70s. So these were not your desktop variety computers we have today, or laptops, of course. These were actually not mainframe computers, but they were mini computers. So they kind of sat in a closet or in a small room, kind of in the corner, about the size of a small refrigerator, mini fridge, basically. But it was a computer that was real popular in the 1970s. And so a lot of the interfaces, peripheral devices, were actually done with some early versions of PICs. You will notice this little quartz window. This actually is the die of the chip in the center, and there's a little quartz window. So this generation here, and I know these really well. This is how I cut my teeth again, doing a lot of embedded systems development 25 years ago. Is if you wrote code for these, you actually used a UV eraser, a UV lamp on your desktop, and you would actually put the chip over the lamp. I guess you could technically have gotten a nice little, tan if you wanted to. So I mean, I actually had a UV lamp on my desk, and it would erase the contents of the EEPROM, as it is, the electrically programmable read-only memory. These were not electrically erasable, not a double EEPROM or flash. This is prior to that, and you actually would erase the EEPROMs with UV light. So if you ever looked into an old computer, if you ever were kind of a nostalgic, looking at like 8-bit guy on YouTube or anything like that, you'll notice a lot of the early day processors that, like, your Color Computer 2 or your Commodore 64, that a lot of the ROMs that are on those boards for those old 8-bit and 16-bit computers, even your early your IBM PCs, all had like a little piece of tape over the ROM. Well, that tape went over the quartz window to prevent UV light from entering the quartz window and erasing the ROM. So they're very easy to use, still very popular today. They have expanded the family. They're not slow and sluggish like they used to be. A lot of the old chips are still available. They are very robust. I mean, robust. I have used these in environments that you probably shouldn't be using a microcontroller, like heavy lightning prone environments. And we need a microcontroller, but it's like anything we toss out there is going to get zapped. These processors can usually handle that punishment. Don't know what is different about them, but these older microchip PICs can pretty much take a pretty brutal beating electrostatically and also just in the environment. And I mean, I guess a lot of it's because they're very slow running. A lot of the old ones ran at 5 volts, so they're kind of slow and powerful in the sense of power hungry. But they work really well. Nowadays, they have little 32-bit ARM-based processor. They bought Atmel, so they own the Atmel family now. They also have their MIPS-based 32-bit core processors I use a lot of. They're really good. And they also have little 8-pin microcontrollers. So does Texas Instruments. So you can get a little microcontroller that is literally an 8-pin DIP. So a little tiny, looks like an op amp, just 8 pins, and it literally is a full-blown microcontroller. Most of the ones I've used, just recently used one actually. It had an ADD converter built into it, had SPI bus built into it. I was able to read an ADD converter, determine a value of potentiometer, and actually write some code to do some mathematics on that, and actually output a waveform to going upstream to a PLC being used in another application. So 8-pin microcontrollers are actually very common. And then there's single board computers. A lot of people in this class, when you're working on your projects, you're probably going to be leaning more towards your single board computers. I'm sure a majority of the class is familiar with this, Raspberry Pis. They're great proof of concept hobbyist platforms. They really are. I probably own about 7 of these. I also own a lot of other basically Raspberry Pi cousins, which I personally lean a little bit more towards because you can use some of them in production environment, such as your Odroids, for instance. You also have the BeagleBone Blacks. That's another hobbyist platform. You have Arduinos and the Arduino IDE. You have the what's it, the Pine series. There's quite a few. In fact, if you go type in single board computer on Google and go to the Wikipedia page, there is a list of all the different types of single board computers out there, and a lot of them are very good and very effective. Some of them have very limited temperature ratings. They're basically rated for the commercial range, which is typically 0 to 70 degrees Celsius. Nothing wrong with that, especially for this class, but if you're designing an industrial-based project, that's not going to work. They're probably also not vibration proof and be able to handle harsh environments. So you got to be very careful where you put a single board computer. Another family I always like to tout because I use them and they are very reliable and very industrial. A little pricey for compared to a Raspberry Pi. But they are very effective is the Toradex line of single board computers. They are very powerful. They have everything from smaller ARM-based microcontrollers all the way to the 64-bit IMX8 8Q Max Quad Max processors that I'm working with now. They have like four 64-bit cores that are active, along with a 32-bit dual cores. I mean, it's an incredible little platform. It includes Wi-Fi and Bluetooth and also LTE. I mean, you can get for something about the size of a credit card for about 100 and some odd dollars. You can get quite a bit of a computing platform running in full up embedded Linux, running full graphics, everything. You cannot even tell the difference between your run-of-the-mill laptop and one of these little small computing platforms. And they are on top of that, they're all silicon. So they don't have, they're all solid state eMMC or solid state drive flash. So it can take harsh environment. It is rated for industrial temperatures. It's perfect for an industrial application. I use those significantly in oil field and gas production type systems where we need a lot of processing power, a lot of communications like dual Ethernet or more. CAN, multiple UARTs, etc. Heavily use those as well. Another common thing is the Xilinx FPGAs. Xilinx are really good for adding FPGA fabric. So you would have used FPGAs a little bit in 248, again in 350, and some of the other classes, probably 449, for instance. Um, FPGAs are really good in having your own custom accelerators, if you will, logic accelerators. So if you're doing a lot of high computational type projects where you got to stream a lot of data through and do a lot of number crunching, FPGAs are great for that, or adding very specialized logical peripherals. And then Xilinx has that also gluing on some ARM processors. Their Zinc-based single board computers are really good. They're fairly priced well for that. Do recommend those as well. They also have the Ultra Scale and a few other new families as well that are very good. So again, tons of single board computers out there. Um, Please check with me early in your project selection. Of course, we're going to go over microcontroller selection in a minute, but check with me if you're planning to use a microcontroller. I try to dissuade you usually from using Raspberry Pi. I know with all of the, if we're still dealing with COVID and you're still trying to, we're kind of limited on interaction and stuff. Yeah, I kind of try to steer you now back towards using a single board computer because it's more likely to have success. I'd like to see you as an embedded engineer. If you're going to be building something as an electrical engineer, doing an embedded system, I like to see you actually learn how to do a microcontroller from the chip level up because you learn the most doing that. And that is actually something that you can promote on your resume as you're looking for your first job because that's actually shines because you actually understand putting something together, not just buying a Raspberry Pi and following the instructions that any high school student can follow and actually do. Because you got to remember, most Raspberry Pis are used in a lot of science fair type projects. So you learning a Raspberry Pi for your senior design project it'll get it done, but is it really going to let you shine? Um, so we can promote you in your career choice and specifically in your resume and in an interview. That's kind of what my focus is for you. So let's talk about microcontrollers for your project. So do you need an MCU for your project? Uh, Probably. Um, you know, this was because I also teach ECEN 215. I give similar lecture here, a little bit more tailored though for your mechanical, your aerospace, your nuclear engine, chemical engineering majors, things like that. They're going to have senior design as well, and more than likely they're probably 50-50, maybe 30% chance. Yes. They're probably going to have some sort of an instrumentation system, so they might be using LabVIEW and National Instruments for that. But for your project, probably yes. And the reason I say that is some point you're likely to be making some sort of control decisions. And so if you're doing that, you need to make sure if you're making a control decision, some sort of a system processing decision, you're going to need to be able to have something to do that. And that's going to be a microcontroller. You're unlikely going to be using a laptop to do this. You could, if your requirements document basically says this shall be performed with a microcontroller, and we're just going to append a bunch of USB, peripherals, basically like a LabVIEW, National Instrument modules all over this thing, and it's going to be fine. And for a proof of concept system, that's probably just fine. But if you're actually building an actual system, putting it in a box, and it's supposed to be standalone and do some little task, whatever this little widget does, right? Then you're likely going to have some sort of microcontroller making decisions. That is very common today. It wasn't so common 30 years ago, but today pretty much everything has an embedded system. Candle warmers have an embedded system in it. Your thermostat has an embedded system in it. Your mouse for your laptop has a small embedded microcontroller in it. Pretty much everything today does, because eventually anything that has Bluetooth connectivity, that Bluetooth connectivity is primarily based upon a microcontroller running the protocol. It's communicating to a radio, but all that communication, so if it has Bluetooth, Ethernet, fill in the blank, it has a microcontroller attached to it. Now, it might seem seamless to you because it's just sort of like an additional little sensor or something, but if it's transmitting information, it's got an MCU. So again, if you're communicating data and having any type of user interaction, you're probably going to need a microcontroller. If you're going to communicate to other systems, in other words, I'm now going to read all this information. I'm going to transmit it via Ethernet over the internet to a SQL database and store it, what we call IoT, Internet of Things, where I'm going to pool this information up, and there's going to be a website that I'm going to interface and coalesce this information and make a report out of it. Yeah, that's a microcontroller. If you are going to take some information and transmit it to a PLC, a programmable logic controller, like an Allen Bradley or something, or a Rockwell, guess what? That's a microcontroller. And guess what a PLC is? It's a microcontroller. I mean, these are just different microcontrollers packaged in different ways. So the big question is what kind of MCU you're going to need, because like I said, more than likely the answer to this is yes. There's very few projects that I've come across where the answer to this is no. So what kind of microcontroller are you going to need? You're likely to spend many hours on this topic. I have wasted many, quite frankly, many weeks on this particular question. So you have to know specifically what your project requirements and specifications are to do this right. This is why we make such a big deal about the ConOps and doing requirements documents, knowing the ICD, knowing all the details of your project before you start making design choices. Because it's these requirements and specs that determine whether or not you can use a Raspberry Pi, or whether or not, even though the Raspberry Pi is a 64-bit ARM processor, or whether or not maybe we should be using an 8-bit or 16-bit, or because of the limitations of some of the I/O interfaces on the Raspberry Pi, it's just not going to cut it. It's not going to be able to read the data fast enough and process it fast enough. Once we got into the cache and once you're at the actual ARM processing core, oh yeah, it'll handle it just fine. Get on the Neon floating point unit. Oh yeah, but you also have bottlenecks, and one of the bottlenecks on the Raspberry Pi is actually I/O. So you need to ask yourself a whole load of questions that are based upon your requirements. How fast do you need to sample your sensors? If you're doing audio waveforms, for instance, am I going to do 20 kilohertz audio, 40 kilohertz audio? Am I going to sample at 40K, 100K? Um, those are critical questions. If you're going to do that with a Raspberry Pi, I can tell you if you're not using the USB port and you're using strictly the SPI I/O lines or just your I/O lines in general, you will not be able to do that. I have run into this countless times because I usually have various audio projects in my class, and someone will eventually come up and say, we're going to use a Raspberry Pi, and I'll tell them, yeah, you're going to run into trouble with that. But they're like, no, 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 I think it'll work. I know it'll work. I saw an example on YouTube where this worked. And so they went and do it, and then they come back about 2 months later and go, yeah, it didn't work quite like, I mean, it kind of worked, but it sounds like crap. The sampling just is terrible. It's distorted. It's fading in and out, and the distortion and the quality of sound. It's just the total. It's just terrible. The tonal harmonic distortion is terrible. What's going on? And it's because of the way it's being sampled. So always pay attention to what are you sensing and why, and what precision, what resolution, and what the sample rate needs to be. Learn a thing called Nyquist. Again, if anyone in here has had DSP, you know what I'm talking about, but that is dealing with the sample rate of a signal. So if I have a 10 hertz waveform, I need to at least sample it at 20 hertz. And that's the bare minimum. Quite frankly, I always do a 10x rule. So if I have a 10 hertz signal, I always try to put 10 points per major period. So for a 10 hertz signal, I will sample at 100 hertz because I'll effectively be able at 100 hertz or be able to reproduce a good faith estimate of what the signal originally was. What kind of communications do you need? Am I doing Ethernet? Do I need to communicate at 100 megabit? Do I need, I'm sending data, 1 byte every, 10 seconds? What am I doing? This really determines what kind of interfaces you need there. What kind of digital I/O are you going to need? What voltage levels does that I/O need to be? This is something very important to be paying attention to with any of these microcontrollers. Most of them are 3.3 volt I/O. Don't be just planning to like, well, I've got 3.3 volt of my I/O and I'm going to connect it up to this 24 volt relay here to the coil and it's going to work just fine. No, it's not. You're probably going to blow up the microcontroller. And then what are you computing? So on and so forth. I mean, what are you doing with a microcontroller? Write it out, put big block diagrams. This is why, again, why we start at the very beginning of the project, big picture. What are you doing and why? What are you trying to solve? What is the problem statement? And then what is the block diagram, and start breaking it up. You do this, this will give you this information. Microcontroller selection. So now let's start getting a little more detail. So now that you got your kind of your specs, use those specs to guide you to the right microcontroller. I recommend heavily DigiKey's website, Digikey, Digikey, Key. I'm sitting here giving this lecture remote, so I got to make sure in my head I don't have I'm looking at a whiteboard here, so it's a little hard. So digikey.com, which is going to be your friend this semester, that and Mouser Electronics. But honestly, DigiKey's website is really good for making microcontroller selections, and not honestly for a lot of part selections. Now, just a plug for Mouser, the reason I like to order from Mouser, just a side note for the projects in here, is because they're in Mansfield, Texas, i.e. basically Dallas area. The advantage of that is UPS is 1 day ground. Here in senior design, we do not order things use UPS red, which means overnight, or UPS blue, which is 2 day. We do not do FedEx. Now, I mean, if you want to do it, that's fine, and you want to put it on your own credit card, it's great. But this department does not order parts overnight. Now, if you want to get parts overnight, if you order from Mouser.com, which pretty much has the exact same parts that DigiKey has, they're 1 day away. So you order at 8 o'clock, literally 7:59 p.m. today, you will have it tomorrow, whenever UPS hits our dock. So that's just a side note there. But DigiKey's website's really good for making microcontroller selection because you can just type in the word microcontroller in the search prompt, and then literally go through basically a peripheral and a pull down list of all of the different sub functions. So if you want these type of peripherals, this voltage level, this speed, this, many bits for the processor, 32-bit or 64. You can do all of that and it'll down select a lot for you. So literally, you want to have fun, type microcontroller DigiKey, see the tens of thousands of microcontroller types, not even quantity of parts, types, different, if you will, species of microcontrollers there are. So use your specs that you've determined to drive this. Do not allow the microcontroller to drive your specs. I have done that in the past. That's where you end up wasting weeks of your time. So if you let your specs drive your microcontroller, you will end up on the right one. So manufacturer series is probably not too big a deal for you here. Whether or not you're using Atmel versus ATmega versus using microchip versus using ARM, of different families like the NXP IMX family, which I'm a big fan of. It really doesn't matter, especially at this stage of your career, unless you've already been using a microcontroller already. Probably you're not specific to a particular family. So for instance, you can get started with the MSP 430 family or the 432 family from Texas Instruments, and it's not going to be any different than if you would have started with the AT Mega family or using a PIC 32 or using an Atmel SAM V7. It doesn't matter. All of them are going to have a learning curve, all of them about the same learning curve. All the tools have about the same learning curve. So guess what? you're you got the same amount of hours dedicated to each one. However, as you get older in your career and you get a little bit more seasoned, a little more experience, you're going to kind of land on a handful of families. So if you're used to using microchip picks, for instance, you're probably going to favor microchip picks for a lot of projects. Why? Because you have the tools and you can instantly go, oh, okay, I know how to hook that up with this pick in about 5 minutes, and I have a solution for you. So you're leveraging your experience. So this is why this becomes kind of part of that. Size of the core. Yes, you can have a 64-bit processor, but if all you're doing is turning on and off a relay based upon a temperature sensor, yeah, you probably do that with an 8-bit. 8-bit's going to be more stable, simpler, cheaper. You can do it with a 10-cent part, or honestly, you can get processors down to about a dime. 10-cent, 50-cent microcontrollers in high quantity. So why throw a 64-bit processor that will do an 8-bit job? Just because you like 64 bits and it sounds powerful does not mean it's a good fit for your project. So make sure you pay attention to what your task is and make sure that the size of the core is appropriate. Don't choose an 8-bit when you're about to do a bunch of double precision floating points. That will be a waste of architecture. You're going to be spending so much time and cussing yourself in the long run. You're going to be starting to kick yourself when you're sitting there going, why am I doing double precision floating point? Oh yeah, I have to. And then I chose this microcontroller. I'm constantly running out of code. You're going to start really kicking yourself for that choice when you probably should have done a Toradex, or a Raspberry Pi or something that had a 64-bit core. The number of cores you may need. If you're doing a lot of processing, you might want 4 cores or 8 cores. And you can actually write code and target it to a specific core. How much memory you need. You can actually make a pretty good estimate on that. You can actually write some of the code in advance. Because when you write the code, a rough version doesn't have to be perfect. It'll give you especially allocate the memory that buffers you need and things like that. It'll tell you how much RAM you're going to need. And then you can actually choose, okay, I really only need 64 kilobytes of RAM for this project, which is actually quite normal. I only need a small bit of RAM for an embedded project. Okay, so I'm going to choose a processor that has 128K. That way I'm assured this is going to work. Same thing with amount of flash. If you need internal, external memory, if you're doing an 8-bit, you probably got internal. If you're doing a 64-bit processor, it probably has external memory. How many cycles per instruction do you need? How fast do I need this processor? Again, your specs determine this. How many I/O pins you're going to need? If you have determined based upon your block diagram, I need 10 I/O lines. I need 3 for a relay, 4 to talk to this one chip, a SPI interface, I guess it's 7, and 3 more to do some other, 3 analog inputs or something. Okay, great, that's wonderful. If there's one change, and that's it, and that's all the I/O your processor has for whatever reason, it only has 10 I/O lines. Use like a 14-pin microcontroller, basically. Well, as soon as one of your teammates come up and says, we're going to add another temperature sensor to this, you're going to have to redesign your entire system. So always look at the amount of I/O pins you need, and always put like a 10%, 25% overage at least in what you need. So you always have room. Yeah, you might have to relay out the circuit board, add a few more lines, but guess what? Now you at least don't have to change the chip, which is good because then all you have to do is add the I/O lines. And then, of course, what kind of peripherals you need. Again, A to D, timers, pulse width modulation, capture, compare, communications modes of different kinds. These peripherals you need to know. Again, what kind of non-volatile storage? I mean, it's just like any computer. You turn off the power, it loses its memory. The RAM, the volatile storage, is wiped. You can't rely on that. So you're going to have things like flash and double EEPROMs that are going to hold your calibration constant, specifically double EEPROM, electrically erasable, programmable, read-only memory. This right here is primarily going to be your for calibration constants. How many ADC counts versus temperature? 212 degrees Fahrenheit boiling is, 2,222 A to D converter counts, something like that. You have a calibration curve in memory or different settings. The set point for this PID algorithm to control this heater is 80 degrees Celsius. Well, that would go in your double EEPROM. Flash is typically your programming code. This is actual flash programmable memory. It's done in programming of blocks. That's where double EEPROM is a little more effective. You can actually program individual cells, whereas flash is done as a block. This is going to be your actual program code. Do you need GPU support? You're doing a lot of number crunching, a lot of floating point arithmetic. You probably are going to use GPUs. Or you're actually doing graphics. Different types of oscillators. If you're doing anything where you're doing timing precise stuff, such as communications, you're doing counting, comparing, or you're counting pulses per second per minute kind of thing, you need a precision oscillator. You don't rely on the internal oscillator. Operating temperature is a big one as well. If you're doing an industrial system, you need to make sure that you're doing industrial temperature range, which is like minus 40 Celsius to at least plus 85 degrees Celsius. Pay attention to that. I'm going to say this is also in the common pitfalls as well. I'm going to say it here. If you're using a Raspberry Pi, order the heatsink. You will need heatsink. Do not think you don't need heatsink. You need heatsink. If you don't order the heatsink, we'll be replacing your Raspberry Pi at some point through the project. I can guarantee it. Because what happens is you start actually processing with the Raspberry Pi, it eventually burns up because it doesn't have a heatsink. It works great. It doesn't get hot when it's sitting idle, but as soon as you start doing actual processing with it, it gets hot. It needs a heatsink and possibly even a small fan. Package and case. Single outline pin, perfectly fine. Dual inline pin, this is through hole, perfectly fine. TQFPs, perfectly fine. QFNs, difficult but fine. Do not, do not, do not, do not choose a BGA. Someone will. It historically happens because sometimes it's the first thing that pops up. I got a really, really great microcontroller. It does everything I want. It's 64 bits. It's got 500 I/O lines. It's got Ethernet. It's got dual Ethernet. It's got HDMI. It's got the graphics port. Everything is built. And basically, I'm describing like an IMX8. Only problem is it's in ball grid array. If you're wondering what ball grid array looks like, look it up. It is literally small ball grid, little tiny solder balls on the bottom of a chip array on a small circuit board that the actual chip is died soldered, hardwired with gold wires to the die, and these little solder pads. Typically on an array of 0.8 millimeters by 0.8 millimeters, and typically somewhere in the neighborhood of 1,000 pads. If you're planning to solder that by hand, good luck. I would love to see someone successfully solder that one of those by hand. I'm sure there is someone at probably some assembly shop that probably can do it with their eyes closed, but I can guarantee you that there's no one in this class and no one in the faculty that can. I know I can. I can do some very sophisticated soldering. I will not touch a BGA with my life. Just not happening. This is typically done with a machine, and we do not have access to one in this department. So do not plan on using this. Now, if you want to go get a board made with a really high-end processor, and instead of buying a single board computer that has one, because guess what, your Raspberry Pi uses a ball grid array. It's soldered professionally by a machine, pick and place machine. If you want to use a ball gray to gray, I'm not going to force you and stop you. I'm going to give you the advice not to do it. But if you want to go to ARQ here in town or Bencor in Brenham and get them to, plead with them or pay them to solder it on for you, be my guest. But you're going to need professional help from BGA. So make sure you avoid that. Also, on just kind of a side note, I'm going to repeat this in the PCB lecture. Do not use O201s. Just do not. O201 packages, do not use them. You're not going to be able to hand solder those. So basics. So first of all, do not write anything in assembly language. I know that there's going to be someone in here of a class of this size. You were really good in ECEN 350. You took ECEN 449, and you think that assembly language is the best way to write programming language because I know how to do it. I'm really good at it, and you may be. There's very few, I say extremely very few people that actually can beat the compiler today. 25 years ago, this was not the case. 25 years ago, you could actually write better assembly language than a modern compiler. Today, the modern compiler can whip you up when it comes to assembly language. They are very efficient because the people who are really good at writing assembly language helped write all of the compilers and made them better and better and better. And nowadays, they are extremely efficient. And quite frankly, unless you are an extremely professional, seasoned pro, probably architecture level of these controllers, you're probably not going to beat the compiler. And there really is no need to. Most of these processors operate at a high data rate, high MIPS, millions of instructions per second. They're way more fat, way more in the speed than you would ever need for probably your project or what type you're doing. And the performance increase you're going to get out of the assembly language in the sense of code space and speed just isn't worth it, even if you were more efficient. So write all your code in C, C++ for most microcontrollers. I usually recommend C for most general embedded microcontrollers. It's kind of the default language. It allows you a lot of the same advantages of assembly language, register level control of the processor, but at the same time and in a high level language. Though there apparently is a debate today saying that C is not quite the high level language because you now have languages like Python, Ruby, and the like. But to be honest, C is a wonderful language for embedded systems. It's predominantly what I write in, and of course C++ for the more advanced microcontrollers like your 64-bit and 32-bit cores. Single board computers are typically, like if you're working a Raspberry Pi, you're probably going to be writing your code in Python, which is perfectly fine. It's just there's now an extra layer between you and the embedded system. The advantage I have also in C is if you're doing what we call bare metal, where you're actually writing the actual code that the processor is actually executing from instruction one, you can use the built-in debuggers, which are tremendously effective. So that's another advantage. Um, Test all your codes separately. Write structured programs. And I'll try to give an example of this as kind of an external aside. Test, write code like an A to D converter module. Read like a function named read A to D converter. Guess what that function does? It reads the A to D converter. Maybe its input is a channel number. Read A to D channel number 1, and a result out of that function is, guess what? The A to D converter value. Really simple. You don't write all your code at once, stick it all in main, and hope it works. Write all your code as independent little blocks. Test each one individually. That way you can rely that, hey, the A to D converter code I got working, and I don't doubt it works. So if you're getting some weird result in your algorithms in your main function of the code, you probably could rest assured it's not that function. Make sure you do GitHub and version control for all your firmware. We emphasize GitHub, but again, I always try to emphasize at this point backing up. Pausing here, back up, back up, back up, back up. This is very important. You need to back up your work. This is beyond firmware. This is all your source code. This is all your design files. This is all of your, say, schematic diagrams, your block diagrams, your Word files, whatever it may be. Back it up. Flash drives, use Google Drive or OneDrive or, was it iCloud? I don't care. Make a backup. The reason why I'm harping here on backing up is A, hard drives do crash. They actually crash a lot more often than you probably give them credit for. I probably, in my personal lifetime, I have dealt with about 5 hard drive crashes. I mean, I'm actually kind of waiting to see on my main development machine. I have a spinning disk hard drive. That's the main data repository. It's like 8 teras. Um, I'm waiting for the day I walk in and that drive's toast. It's going to happen. It's not a question of if, it's a question of when. Um, that entire drive is backed up by another drive, and it's also backed up externally with a backup service and a few other things. And I also use Google Drive. So when it does happen, I'm not losing any sleep. I have actually walked in and had the dreaded phrase, and I don't know if you've ever had it. Please insert boot media. Anybody who's ever seen that phrase knows exactly what that means. That means the hard drive on your laptop or desktop is gone. The BIOS cannot find it, and it needs something to boot. And the thing that should be there to boot, i.e., the hard drive, is no longer present in some form or fashion. That is a very big sinking feeling if you haven't backed up. I learned this the hard way 25 years ago, and yeah, since then I've been pretty religious in backing up. So, and again, the reason I bring this up is, does this happen in senior design? The phrase, the dog ate my computer. Yeah, it's happened. I had one last semester actually, where I had one student call up and say, Professor Lusher, you're not going to believe this. I know you warned about this, but I did this entire circuit board. He wasn't even doing the embedded system, mind you. I did my entire entire DC to DC converter circuit board in Altium. You saw it. I presented it the other day. All those files are now gone. My laptop crashed, and I don't. We went back and forth for about an hour. I think in the long run he was able to salvage it, but it took 3 weeks and a lot of effort. In the meantime, he's like, "What do I do?" He says, "Well, I guess." I asked him, "Do you have a backup copy?" No. You didn't put this on a flash stick? No. Do you have a backup copy on a cloud drive somewhere? No. Is it in GitHub somewhere? No. The only copy was on the hard drive of my laptop. And he goes, "What do I do?" Because it was towards the end of the class. So I was like, well, there's only one thing you can do. That's rebuild, restart from scratch, rebuild it. He didn't like the answer, but he did. Personally, I've had that happen to myself. My favorite story was 23 years ago. I was working on a voting system, an early electronic voting system way back when. I was writing code in Visual Basic, which was a very early version of Visual Basic. I wrote a bunch of code and had the entire project, and I had finally had everything up and running. I was pretty much done with the new changes I was making. Um, I was cleaning up some files, and it's like, oh, okay, I've got everything cleaned up like I want. I went to hit, play to debug the project, and I started getting some weird results. I mean, just bizarre behavior, completely like weird stuff. Like, it shouldn't be doing this. What's going on? I'm getting these weird memory errors and can't find this error. What's going on? Finally, after about 10, 15 minutes, I finally dawned on me that the files that had a lot of the program code and background functions were deleted. Now, I had a nasty habit and still do have this habit of when I'm getting in a hurry and I start trying to do delete, I don't hit the delete key. I hit the shift delete key. And if any of you Windows experts in here know, shift delete is delete permanently. I mean, like, delete it. And I mean, of course, you can usually use undelete type programs to recover that if you haven't had any drive overrides after a while. I've been there, done that too. So I had hit shift delete on an entire folder worth of support files. Yeah, pretty bad. After about an hour or so of sobbing and crying and pitching a fit and going, what have I done? Guess what? All of that doesn't matter. The files didn't magically reappear. You kind of have a dawn of a reality hit you. And guess what I did for the next 6 hours at midnight? I basically stayed up all night and rewrote all of those support functions from scratch, from memory. and proved, in fact, improved upon things in the end, and learned a valuable lesson. A, please don't hit Shift Delete. B, because I didn't have a backup of any of that directory. Backup directories often completely have backups. If there would have been a thing like Google Drive back then and I was using it, which is what I do nowadays for all my production files, guess what? I would have just hopped on to Google Drive, say go back to previous version, boom, files would have been there. So please consider that. Backup basics. Okay, so we've talked about backing up. So learn from others before you. This is another big one. This is something very important, especially after you graduate. Is don't try to just bang your head in the wall and try to solve something all by yourself. There's a ton of forums out there. Use them. Go to, if you're in 403, talk to teams that are in 404. They've already been there and done this part of the project. So talk to them. Talk to me, talk to Stavros, talk to Kevin, talk to your TAs, talk to other professors, watch YouTube videos. I can guarantee you'll buy books. I have more books than you can count. Um, Look at previous projects. Always talk to someone. In fact, most of my stuff I have learned from friends, my mentors and stuff. I have learned, hey, I'm working on a DC to DC converter for this project. What do you recommend for something like this? And guess what? They give you the answer. It's not cheating. It's not stealing. You're getting help. There's nothing wrong with that. That's what I like to see you do. Also, learn your IDE, your integrated design environment. If you're going to be using, for instance, Microchip PICs, and you're going to use MPLAB X, please download MPLAB X early and learn it. Don't start learning the tools basically the day that you need your tools. When you actually start writing the real code for your project, you want to have already done Hello World and the basics. Of course, just kind of going back to what we talked about earlier, test all major subsystems for your system first. Your A to D, your D to A converters, any temperature sensors, all the core functions, timers, counters, whatever it may be, peripheral PWM. Test each of those subsystems completely separate first before attaching it to your main function. Write simple, basically hello world tests. Literally prove the communication systems work by doing a star thrower where you send out asterisks. Very important. Use your integrated debugger. Again, not very easy to do with a Raspberry Pi, but if you're using an IMX6 or a PIC32, guess what? You've got an integrated debugger. Use it. It's powerful. You watch variables and stop breakpoints, triggers, all sorts of cool stuff. Plan for extra I/O and performance is always a very good thing. And use a watchdog timer. Watchdog timer is basically a small timer whose sole job it is to sit there and monitor that you reset it. So your main code body will reset the watchdog timer. And if the watchdog timer times out, say it's a 100 millisecond timer, after 100 milliseconds, if it's not been reset to 0, after 100 milliseconds, it will reset your main processor line. This will save your actual industrial project from causing catastrophes because at least within 100 milliseconds, if you turned on a pump because the program, there was a spurious noise and the program counter jumped, and all of a sudden you're executing a bunch of bad code and a bunch of I/O lines turned on, and you started turning on pumps and servo motors when you weren't supposed to, at least after 50 or 100 milliseconds, whatever your timeout time is, it gets caught and reset. Comment your code. Use variable names other than X and var. And I didn't just pull this out of the air. These were real variable names in projects that I have reviewed. And X not being the x-axis of something, or variable X meaning, truly the variable X. X being like temperature or casing pressure. X meant nothing. They just used the letter X. Use structure programming and modular design as great examples of doing that. Use a block diagram or a flow chart when possible. I personally use a lot of block diagrams. Flow charts work. I've done a lot of coding based upon flow charts. When I personally write systems, I use block diagrams. Have a document describing how the code functions at a high level. That's basically a block diagram plus pseudocode. This is what I do. And of course, if you use a third-party API toolkit, great. There's nothing wrong with using the library. Just document it. Give credit where credit's due that you used it and that you didn't write it. And 2, the programmer that's going to be coming behind you eventually needs to know that you used it so that they download it as well. Embedded OS versus bare metal. Well, bare metal just simply refers to the native code. The code running on the microcontroller is your code nothing but your code. There is no operating system. There's nothing between you and the I/O pins and the peripheral units other than your code. Embedded operating system can be any type of operating systems for any supported microcontroller. Common things are embedded Linux, um, Android, Noobs, and this is off of the Raspberry Pi. Raspbian would be a good version of a Linux, for instance, in a Raspberry Pi. Yocto builds, YOCTO, is a real common open embedded Linux for a lot of microcontrollers. Windows actually has a version for Raspberry Pi, strangely enough. It actually works halfway decent. Advantage of that is you can actually write code for a Windows tablet, like a Surface. You do a Windows Universal program, and it will work for IoT. It's pretty nice. There's various real-time operating systems where you need real precision timing. There's an actual definition of what real-time is. You're likely not going to need this, but if you're doing real precision timing in a future project, this will probably be useful. So embedded OS, what are the advantages and disadvantages? So first of all, embedded OS is wonderful because it has a rich set of API functions. All your TCP/IP functions for Ethernet are already built in. All probably if for instance I'm thinking of embedded Linux, for instance, CAN functions for control area network basically all these communication buses, SPI, I2C, so on and so forth. All those functions are built in. You still got to write code to support what they call the API, the application programming interface, which may or may not save you a little bit of work. Some of these peripherals are so easy to use that really the API function is not really just more of an extra step you go through. But if you're doing TCP/IP functions, unless you have a library for it, you have to write that code. So it's kind of nice to get it already existing. All sorts of third-party tools. A lot of encryption algorithms and things like that already done for you. You don't have to write it yourself. You just focus on the application layer. So you can run multiple applications at once. Linux is already built to do multi-threading, multiple processes at the same time. So you don't have to do anything special there. You just basically whatever you can do with Linux, you can do with your embedded system. So main advantage of that also is being that it's embedded Linux is if you know Linux, then you already know your embedded system interface. You literally go on the console port. Usually one of your UARTs is your console port, and you go on to TeraTerm or PuTTY or some other serial port interface, Minicom, and you can actually talk to your embedded system as if it was a Linux box, because that's what it is. It does provide a disconnect between the hardware and the application code. And I would also say, kind of correspondingly, that is also a disadvantage, is that correspondingly, it is a disconnect between you and your application code and hardware. So that can work both ways. Um, the nice thing about it being disconnected, if you're doing a lot of communication stuff, that's not really a big deal. If you're doing a lot of hardware level functions, that disconnect can sometimes be a little bit awkward because you're actually trying to control a specific I/O line or a specific peripheral in a microcontroller, and having that direct connection is advantageous. It does consume more processor resources to run an embedded OS. I mean, just by default, you have an entire set of APIs and overhead now over your particular application. And so if you don't just, kind of customize the kernel in the case of Linux correctly, might end up with what we call bloatware. We have a bunch of drivers and a bunch of services that are firing that you don't need. You'd be firing NTP update, network time protocol update, and the thing's not even connected to the network. And just because you didn't disable it, this application's constantly looking for internet access that doesn't exist to update the system time. That consumes clock cycles. Kind of becomes annoying too. So that's something to pay attention to. Bare metal advantages. There's zip between you and between the application layer and you. You are the application. I mean, it's it. The very first instruction is your instruction. Now, granted, it's compiled from your code, but it's still your code driving it. There are technically no unknown code elements. I mean, if you're using a library, you might want to learn a little bit about the library. But technically, if you wrote all of the C code, which a lot of my smaller embedded projects, every bit of the C code I wrote. So the advantage of that is if it's doing some weird behavior that I'm not expecting, it's my fault. And I can go fix it. That's also the advantage. It also has very predictable performance. It's going to do exactly what it's told. Every clock cycle is very predictable. It's usually a less complex design. I mean, it is the code that you have there. All of the header files and the C files combined in one project. That's it. There's nothing else. You can load it in those flash to the CPU and you're done. And because of that, it's instant boot. The very first instruction is your application code. So you could do things like instantly set all of the I/O lines correctly and things like that. Now, in the embedded OS, for instance, with Linux, usually the first application is U-boot, which is the just kind of the same thing as BIOS on a laptop or a PC. That's the instant boot part, and you could write your own U-boot. I do as well. I have code to actually write U-boot. It's actually part of when you develop a Linux kernel from scratch, which I've done a few of them. Um, so you can create a U-boot, and part of the U-boot is you can do, since that's the instant boot part, if there's some specific hardware functions that need to be done on boot, you can do it there while the kernel is loading. So it usually takes several seconds for the Linux kernel to load, somewhere in the neighborhood between 2 to 6 seconds for the kernel to completely boot. So that's kind of good that U-boot takes care of some of the basic I/O. So disadvantages: all library and tools must be included in the project. So in other words, again, there's nothing between you and the application. You are the code. You are the code. So you have to do that. So if you're doing multi-threading or multiple applications if needed, multiple like core 1 is going to be processing sensors, core 2 is going to be processing communications and sharing memory, you can write two separate programs, aim one program for core 1, aim one program for core 2. Yeah, and perfectly fine to do that. Do that all the time. You're just the one doing it. You can actually, in the compiler, specify that, and then actually it will link and build and flash and load the appropriate program into the appropriate core. All that's done for you at the compiler level, but you are responsible for it. So common pitfalls. Biggest one is not selecting the correct microcontroller based upon your project needs. Again, always go back to your requirements and specifications documents, your ICD. All of these documents mean something. Look at that. If you need to have someone look over it with you, please go to your TA or go to me or go to Kevin Stavros. We can help you there. Writing your full application without modular design. In other words, you just write main.c, everything is written at once. Disadvantage, it makes your testing very complex. Advantage, it's done. Good luck debugging that. Because I've done that, and you quickly start cutting and pasting your code out and go back to the basics real fast. Not planning for extra resources like extra I/O or some sort of debug port. Like for instance, I'm not going to need a UART from a project. I'm just turning on and off a sensor. Plan for a communications port. Just saying. Because a debug communication port, you can actually send out little strings to let you know where things are, and maybe you can pause things. You can manipulate your program a little bit at the debug level with a simple RS-232 UART port. It's very useful. Not using a debugger. Again, at the hard embedded level, at the microcontroller level, if you're not using a debugger, and you have one available for you, you're being a little bit foolish. Debuggers are fantastic devices. They'll let you stop, again, look at variables while the code is executing. So it gives you a snapshot of what exactly is going on at the embedded level. Common other pitfalls: using the wrong voltage or current on I/O pins. Again, turning on and off a relay that consumes 100 milliamps and using an I/O line instead of a transistor to drive that, you'll blow out the stage. It might work a few times, but eventually that I/O pin is going to blow, and you're going to wonder why your project no longer works. The phrase I end up here: "It was working yesterday. I don't understand." And I go take a look at the schematic, and you're direct firing a relay. That's why. Eventually you'll wear out the transistor. There's not enough memory. I planned for 1 kilobyte of ROM. I'm fine. I calculated exactly what I needed. I needed 928 bytes, and that's all I needed. So I know it's a foolish scenario, but or silly scenario, but always plan for a little extra memory. Always. Wrong sample rate on ADC to DAC. This one's again really common. You're planning a certain signal you think is going to work with the analog digital converter you picked, but you didn't really think about the sample rate. You didn't bother to comment in your code. This one is extremely common. I even have this with my graduate students. that I have working with me on projects. I go look at code and I'm starting to decipher what I'm reading. They're using variable names that don't mean anything. There's like one comment for every 5 lines or 10 lines of code. I don't know what's going on. Please, I comment every line. I mean, I will admit I'm an over commenter, but when I go look at my project 2 years from now, I know exactly what it's doing. So please comment your code. Not using watchdog timer, we kind of bang that one pretty good. And again, this one highlighting back to what I mentioned earlier, no thermal design. In the end, microprocessors, microcontrollers, they generate heat. It might be a small amount of heat, it might be a watt or two or half a watt, depending on what's going on, but there is heat being generated. If you put that in an enclosed space with no fan circulation or no air venting of any kind, eventually that heat builds up and will destroy the chip. So make sure there is some sort of ventilation or some way to reject the heat. And the biggest ones, I say this is probably the number one set of problems, is making assumptions, just assuming that things are going to be a certain way. Don't do that. Get facts. Don't just guess. And then not asking for help and advice. That's probably the number one thing. In fact, if anything in this class I want you to walk away with is that you walk away with knowing how to ask for help and advice. That is the number one thing that we're trying to teach in here, is that you asking for help and advice. So that's sorry for the long lecture on microcontrollers. Hope this kind of clarified some things. If you got any questions or concerns or want a little bit more explanation, please let me know. Else, have a wonderful day, and I will talk to you soon. Bye.